Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. In the previous session, we've talked of internet measurement and how it's very important for both end users and for network operators. Currently, internet measurement is a very active area of research, making high impact research contributions. But it was not always like that. In fact, there was a time in which there were minimal number of measurement-based papers that were proposed. In fact, a study was conducted in 1988 and it basically analyzed papers over 2 decades, which is 20 years, and they discovered that only 50 papers were there which were measurement-based, in contrast to thousands of papers which were queuing theory and modeling-based. We must remember here that measurement is just a tool like simulation and modeling is for analyzing network performance. However, it is more difficult to perform because you need access to devices. You need a physical network which has been constructed, and then you need to instrument it and measure it. In contrast, it is easier to do modeling and simulation because in many cases you do not need to have a physical prototype. You can simulate anything in software, and because of that there has been a preponderance of research which is modeling based. But this has now in a way overturned, because now a lot of focus is on measurements, because it has been shown that if we rely too much on simulations, then it may be that because simulations make many implicit assumptions and they are based on the data that we have. So the findings from simulations may not match very well with reality when we try to extrapolate simulations into settings about which we have no measurements. So currently, because of now the focus on measurements as the tool of choice of validating network research, a lot of platforms have been established for publishing measurement-based networking research. And I'll name just a few. There is the Passive and Active Measurement Conference, and there is the Internet Measurement Workshop/Conference, which has been a very popular platform since 2000. And it has been since 2000 that a lot of progress has been made in understanding the internet. Now the question is, what have we gained from the understanding of the internet by all this study? So to understand even this, we need to see that internet is a moving target. It is not going to remain static. In fact, internet is increasing and growing at a phenomenal rate. It has sustained exponential growth over an extended period of time, and the traffic it contains and it carries is changing all the time, with new protocols being discovered and the previously most popular protocols going down in popularity and newer protocols coming up. So because of this, we need to realize that many of the findings of some of this research will not apply to the future internet, but still a lot of it would, and that is the part of the research that we want to focus on. We would call this part of research as the invariants of the internet, that we've seen that across many studies we find and we've replicated such findings, and we want to focus on that. And we also want to focus on some trends, and trends are predictable ways in which the internet is evolving, and this would be the foundation on which we want to base our understanding of the internet. So with this background, let me now tell you about the structure of today's session. Initially, I'm going to talk about main internet measurement results, and I'm going to talk about 3 particular sections of internet measurement research. I'm going to talk about results that apply to traffic that moves on the network. I'm going to talk about applications that use the internet, and lastly I'm going to talk about the results that apply to the infrastructure of the internet. In the second part of this session, I'm going to talk of some sound measurement techniques which have been proposed by one of the pioneers of the internet measurement discipline, Vern Paxson, and I'm going to talk about some of the guidelines he has given about making sound internet measurements. We begin with the first part. In the first part, I'd start by talking initially about traffic and network monitoring and the internet measurement result that relate to this topic. The first major finding I'm going to share with you is a paper by Carey Williamson, who wrote this in 2001. And he wrote 10 basic findings about the internet, and I'm going to go through each one of them, and we'll then see if these findings actually hold for the modern internet, because it has been some years since 2001. So the first thing is TCP accounts for most of the packet traffic on the internet. Many studies have shown that TCP is actually bulk of the traffic that is carried on the internet. There are many protocols that actually use UDP, protocols like DNS, protocols like SNMP, but still the popularity of TCP may be explained in the context of the popularity of the World Wide Web. We know that TCP is used by the Hypertext Transfer Protocol, the HTTP protocol, and probably this is the reason that most of the traffic on the internet is TCP. But I will point out here that, for each one of these points, I will comment on, if these findings do still apply in 2010s. So currently, due to the proliferation of peer-to-peer traffic, most of which runs on UDP, it has been seen in many studies that now the balance is kind of restored, and in some cases even UDP has the bulk of traffic, but across many studies it has been seen that TCP has more of the share of the bandwidth. The second point, and I'm going from bottom up, so the ninth finding is that the traffic flows are usually bidirectional, and the major point here is they are bidirectional, but they are asymmetric, which means the property of the forward path is not the same as the properties of the reverse path. This was first brought up in the PhD thesis of Vern Paxson, who discovered that the internet path across many different paths have a lot of asymmetry. And this was then replicated by a lot of studies. And we now consider it to be an invariant. We think of this as a common fundamental insight about how networks work, that if the networks are large, typically the forward path and the reverse path will not be the same. It may be that the forward path and the reverse path, even when we talk of routing, they're taking different directions. And we did not cover this in traceroute when we studied the active measurement tool traceroute, but if we use traceroute, it is just measuring the path it takes as you go from your machine to the destination. But the destination may be using a completely different path to route its message back to you. And this is what we mean by asymmetry. Even if we don't have different paths, it is often the case that even on the same path, because routers have different interfaces, and you would be traversing different interfaces on the forward path, and while you're coming back, you would see that the queues and the loads would be different, and because of that as well, you would see different queuing delays. The third or the eighth point is that most TCP connections are short-lived. In fact, in this session, later on, we would be talking about this in more detail, but it has been seen in many studies that most TCP connections are only short-lived. So they would come up, they would take 2, 3, 4 seconds to do the transfer that they want, and then they will complete the connection or close the connection. So this is again, this is probably another invariant which has been it has shown up in a lot of studies. Another important point is about the Poisson modeling. We've seen when we talked about fractals that internet traffic inherently has a fractal nature. And aggregated network traffic, it has been shown, unfortunately for network designers, that it does not have Poisson characteristics, because Poisson traffic characteristics are exemplified by independence, and it has been shown that network traffic has long-range dependence and correlations over longer periods of time. And because of that, the packet arrival process is not Poisson. I would like to stress and make the distinction that the packets are not coming according to a Poisson process, but the sessions do come according to the Poisson distribution, and this has been shown in many studies. The difference is that in any given session, you're going to create and send a lot of packets. If we look at the level of packets, the distribution that they have is not Poisson, it is usually heavy-tailed. But if we look at the distribution of when the sessions are coming, for example, at a web server, when a new flow is being opened, then it has been shown that this can be modeled as a Poisson distributed random variable. Okay, another thing which has been shown is that packet sizes are bimodally distributed, which essentially means that two packet sizes are more popular than the other packet sizes. And these packet sizes, the first mode is at approximately 40 bytes, which is a simple acknowledgement packet coming back which has no data. So you have 20 bytes for the IP header, 20 bytes for the TCP header, and you have no payload. So this is why we have 40 bytes packets, and also you have 1500 bytes packets, because that is the MTU defined by Ethernet and some other link layer technologies. And beyond this, you also have other packets. It's not that you only have these two packet sizes and you do not have any packet sizes. In fact, every time you make a transfer, the last packet would probably be somewhere between this, and this would be according to the amount of data that you have to send. But most of the traffic is carried in two main packet sizes. It was true for the internet that was there in 2001. If this is still the case, probably we need to do more research. In some cases, we have seen that we have 3 modes, and there is another mode which is close to 500 bytes. But what we can talk about is that packet sizes are not normally distributed. They are either bimodal or they are trimodal, and this is one thing that we can learn from many findings on internet traffic. Another thing is we want to talk about is that packet traffic is non-uniformly distributed, and this goes to the Pareto principle. In some of the causes have most of the effect. So even in internet, it's not that traffic is uniformly distributed. Another point is that network traffic exhibits locality, and this locality means correlations. So these correlations may be over time series, in which case we would call this temporal locality, or it may be over some geographical space, in which we would call this spatial locality. Also, as I have alluded to earlier, aggregated network traffic, especially if we're thinking of the very small time scales, they have fractal nature. And probably one of the most relevant finding, it's pretty much an invariant, and it continues to be that way, is that internet continues to change. It's not going to remain static, and we'll be seeing soon enough that many of the internet traffic statistics do not remain stable as well. So if you measure something, it may change completely in the next month. So in that sense, internet is very volatile, but we still have some stable properties, and many of them were covered in this slide. Let's talk some more about invariance of internet traffic. Now I'm going to refer to a paper by Vern Paxson and a co-author Sally Floyd, in which they talk about simulating the internet and difficulties in that. But still, although the topic relates to simulation, the issues also apply to measurement. So they came up with some points, and I'm going to talk about them now. The first invariant that they've discovered about internet traffic is that most internet traffic has diurnal pattern of activity, which basically means that you have some daily pattern. During the night time, you would have the traffic waning. When the morning time comes, the office time, the traffic would increase, and then it would keep on increasing probably until you have a dip in the lunch office hours and so on. The idea is that you have some definite pattern that repeats after every day. I'm going to show you graphically the same thing later on in this session, but not only do we have daily patterns, but we also have weekly patterns. For example, the usage of networks on a Sunday would not be the same of the usage of a network on Monday, typically. So this tells us that this thing is going to repeat after every week, and this is known as a trend. So if you recall, I've mentioned an invariant, a property that does not change. And I've also talked of a trend, which is predictable change in the characteristics of internet traffic. So one predictable trend is that you would have diurnal and weekly patterns, and the data is not stationary over extended periods of time. We may represent the data by a stationary model in smaller time scales, but when we reach in the time scales of hours and of the time scale of days, we would see that the data is no longer stationary, or it cannot be appropriately represented by a stationary model. Also, we have seen that network traffic, especially aggregated network traffic in smaller time scales, it has self-similar properties, and this was covered in much detail when we talked about the fractal nature of internet traffic. One thing that I've talked about earlier, and which was also covered by the paper by Williamson, is the Poisson nature of the session arrivals and the non-Poisson nature of the packet arrivals. Also, it has been shown in many different studies that connection sizes, connection durations have a lot of variation, and they are not well represented by some distribution with mild randomness. So for example, normal exponential distributions are not good models for wild randomness. Instead, we can use log normal distribution, which would represent the data in an analytical form, and it has been shown that log normal distribution is a good model for connection sizes and durations in many different studies. We must remember that log normal distribution, or any distribution, is after all just a model. It is not the reality. So you would always have some misfit, and that is typically the case in the upper tail. So in the very extreme values, you would typically have a mismatch between log normal distribution and the empirical data. So we must be careful about that. Another important point highlighted in the study of Vern Paxson is the invariant characteristics of the global topology. So there are many things that we can predict about an internet because we understand its association with geography. For example, if you have a link which is from Pakistan to the US, then you have some expectation already about the delay that you would expect. For example, the delay would not be 5 milliseconds because you have a lot of distance to cover, and the propagation delay would ensure that you have higher overall delay. So, and similarly, based on the geographical pattern of different nodes, and due to the fact that it is us humans who are using these computer networks, we can already infer a lot about the traffic that will occur on the network. For example, if we have a network which is only operated by a user in your office, and your office is only from 9 to 5, then you can already predict that this would be the time in which you have a lot of load, and after that the load would be very low, or even it would be non-existent. But if you have a global network in which people from all over the world are connecting, then depending on the relative distribution of the audience, you would expect a sameness around the day, especially if you have a global audience. So these are some of the invariants which have been proposed by Vern Paxson in his study. Okay, let's now talk about some network traffic interactions. We can see that in many cases we quantify the performance of internet in terms of delays experienced on various links. And these delays can be further divided into two components. One is the deterministic component and the other one is the stochastic component. The deterministic component is something that does not change. For example, every time you do this, the deterministic delay would be the same, but the stochastic component is going to change. So let's study the deterministic component of the delay. The deterministic component is essentially composed itself of the transmission delay and the propagation delay, which are in a sense constants. The transmission delay is the delay it takes to take the packet and put on the link. And this is a function of the transmission speed of your network interface card. And this is a static value which is not going to change. The other static value is the propagation delay, which is a function of the distance of the link connecting you to the eventual destination. So we can say that this is the deterministic component of delay. And how do we measure this? If we want to measure the deterministic component of our round trip delay, we can make many measurements and take the minimum RTT as an estimate. Because in addition to the deterministic component, you also have a stochastic component which is composed of queuing delays. So if the queuing delay is 0, then all you have is the deterministic component. And because of that, we assume that if we take multiple measurements, one of them would give us a value in which the queuing delay is negligible. The stochastic component, as I've just mentioned, is composed of the forwarding delays and the congestion events in which you form queues and some of the packets have to wait. And the amount of wait is random because it depends on the other traffic that is also incident on that particular router or that particular device. So because of this, we can call this a stochastic delay. And to model these, we can make use of many long-tail distributions that exist. And typically, Weibull distribution and Pareto distributions are good models for this stochastic component of the queuing delay. Okay, let's now visually see the results as they relate to traffic models on sub-second time scales, time scale of microsecond till seconds. And we've covered this when we talk of the fractal nature of the internet. There has been work on this by researchers in 1990s by Leland and his team, Walter Willinger and some other researchers. They worked on the famous Bell code trace data, which was a very high resolution Ethernet trace file, and they discovered that over large different time scales, the aggregate nature of traffic has a self-similar nature. And this can be seen on the slide now, where you see that for various levels of aggregation, the graphs have relative similarity. They are, in a statistical sense, quite similar to each other. And because of that, it has been proven again and again for many different kinds of traffic, for LAN traffic, for WAN traffic, for World Wide Web traffic, for video traffic. The internet traffic in all these different scenarios and all these different manifestations are self-similar. So if you want to analyze some algorithm, some protocol of yours, and you want to subject internet traffic as a workload to this, you must incorporate self-similar models in your simulation. Otherwise, your simulation may lead to misleading results. If we consider larger time scales of minutes and hours and days and years, we would see that now the self-similarity pattern goes away, and instead the trend appears of the diurnal pattern and the weekly pattern. And now the data becomes non-stationary, in that it cannot be represented by a stationary self-similar model. So as you can see on this slide now, that you see that there is a definite pattern. If you see the figure above, you would see that there is more traffic during the day, and as we approach the midnight, the traffic starts to wane, and it keeps on doing that until we get to the morning hours. And this is typically the case for all ISPs, and it depends on the kind of market that you are serving. But typically, because ISPs have geographically limited audience, so they would have such a daily pattern. Even as we look in terms of weeks, you would see that even in weeks you have some pattern, as discussed earlier. The weekends typically would have lesser traffic. And even over further extended time scales, even over months and years, you would see that traffic is not stationary, because internet is not stationary. It keeps on changing. And because of this, we can measure the network, and on the basis of this, we can see how the network is evolving, and we can project the rate of evolution to make future predictions about how the network would be. Also, it's important to know these trends, because when you're designing some new protocol or when you are designing some new algorithm, you don't want your design to be obsolete in a few months and in a few years. You want it to be scalable. And for that, you need to customize your work if it can be customized to all possible workloads. But in many cases, we have trade-offs. So then we need to study the workload that you would be subjected to, or your algorithm, your protocol would be subjected to, and then you make projections of how things are going to evolve, how things are going to change, and then on the basis of this, you make your engineering design choices. Okay, we've talked of diurnal and weekly patterns of internet traffic. Another important point about internet traffic is that it has a lot of statistical variation, and this variation is not of the mild randomness type. If you recall, we talked of mild randomness and of the wild randomness, in which the variance or the variation is over many orders of magnitude. In the internet, the variation is in fact over many orders of magnitude. It's not like simple quantities like height, in which everything revolves around the central value. In the internet, you can have value which is 10,000 times more the average value. And also, as a result of this, and as a result of the constant evolution of the internet and of the traffic mix which is going on the internet, you see that most of the statistical metrics become unstable, in the sense that we cannot really say for sure that what is one statistical measure which defines this internet, because it may be that in the next month everything changes. As an example of this, let me show you some results from Vern Paxson's work at Lawrence Berkeley National Labs, in which he was employed, and he did a lot of work of internet measurement in. So he was measuring the amount of FTP traffic exchanged, and he measured this for many different months. So results are shown for March 98, and then from all that distribution, he thought that, okay, let's think of the most stable statistic that we can have to describe this empirical data. And we know that median is, in the usual case, quite a stable statistic, because it is not affected by outliers. So the median file transfer size for March 98 was 10.9 kilobytes. When this was repeated some 6 months later, it was seen that now the median file transfer size has halved. It has become 5.6 kilobytes. 1 year later, again it was back at 10.9 kilobytes, and another 6 months later it was seen that now the median file transfer size is 62 kilobytes. So you see that now the median is not stable, it is fluttering around, and this is because the nature of internet traffic is such. So we need to be careful, and this can be thought of as invariant, because this property of wild randomness shows in a lot of different places in network performance evaluation studies, especially in the context of workloads. Okay, let's talk now about the distribution of workloads. We've said that it is having a lot of statistical variation, and we usually use long tail distributions to capture such variance or such variation. So as an analogy, the researchers have come up with different ways to describe how you have a lot of statistical disparity or a lot of statistical variation, and they have defined and they have discovered that this statistical variation is not just in size of something, because typically we associate this concept of long tail distribution with just sizes, but it is also concerned with the lifetime of a connection. And to make things easy to understand, internet researchers have proposed analogies. When they talk of size, they say that you have some very large file transfers, and we call these file transfers as elephants, and you have a lot of small transfers, and we call these mice. So the idea is that you have very few elephants and you have a lot of mice, but even with that being the case, a single elephant is equal to a lot of mice. So because of that, one outlier or one value in the upper tail is going to significantly change the statistics that you calculate. So this is typically the case for file size, for bytes transfer, and so on. We can also characterize the statistical variation in terms of lifetime of connections. And we have seen earlier that TCP connections are usually short-lived. So there has been a lot of work in this, especially by Neville Brownlee, who discovered for the traffic that he considered that 45% of the traffic is short-lived. And again, in the tradition of internet researchers, he gave the analogy of a dragonfly, which is very swift. So in the sense that it comes and goes. So 45% of the connections last for less than 2 seconds. And on the other hand, the tortoises are those traffic flows which continue even for length larger than 15 minutes. And these are very small in number. Neville Brownlee calculated this to be just 2%. But he also calculated that just this 2% contributes around 50 to 60% of all total data bytes. So we see that there is a lot of data variations, and I hope the terminology and the phenomenon of elephants and mice and of dragonflies and of tortoise has made it easy for you to understand. Let's move ahead and now wrap up the discussion on network traffic by talking a little about measuring worms. Worms are malicious programs that infect other computers by propagating over networks. And this is mainly used for malicious purpose, and it creates a lot of unnecessary traffic, and it clogs up the links unnecessarily. So we want to thwart all such attempts of using worms to create unnecessary traffic. So in the physical case, when you consider the biological worm, if you want to prevent yourself from being infected from it, you need to vaccinate yourself. In a similar context, we need to vaccinate the computer systems that make up the network. In that, we need to give them proper updates so that if they have any security vulnerabilities, they may be removed. So in a similar light, just like we consider how epidemics are spread, the computer networking researchers also use similar concepts to study how the worm spreads across the internet. And there has been a lot of work in this area, and Vern Paxson, who we've talked about repeatedly in the course of these two sessions on internet measurement, he is working a lot on detecting and defeating worms. So he is also known as a wormologist. So this is one active field of research in which a lot of work is being done. Now let us talk about application properties. Up till now we have talked about the network traffic properties, but now we're going to talk about the measurements that only relate to applications that are using the internet. So the first and probably the most important application that is run on the internet is the World Wide Web, or the HTTP application. And it has been shown by Mark Crovella, another person who has done a lot of work in internet measurement and who has a book on internet measurement. It is co-authored by him and Balachandar Krishnamurthy. It's titled Internet Measurement, Infrastructure, Traffic and Applications, and most of our lectures are actually based on his work. He has discovered that World Wide Web traffic has basically a heavy tail nature, and it can be modeled as being structurally created from an on-off process, in which the time we spend in the individual on and off stages are heavy-tailed. So if we have this, and if we aggregate many of these sources, we would see that the HTTP request patterns and the various file sizes and all the parameters associated with World Wide Web, they would start showing heavy-tailed behavior. And research has shown that if we want to model different workload parameters as they relate to World Wide Web, we would require different distributions. So let's talk about this. If we want to model session inter-arrival times, so we're talking inter-arrival time. So this would be modeled by exponential distribution. So response size, the resource size, the number of embedded images, the request inter-arrival times are all modeled as Pareto distribution because they have a heavy tail nature. Also, response size, resource size, temporal locality, they are represented by a log normal distribution, which is known as a long tail distribution. It does not have infinite variance like some of the Pareto distributions, but it has still a property in which you have a kind of a long tail. So besides this, if we want to measure the resource popularity in terms of ranking of various files that you have in terms of popularity, then we can use a Zipf-like distribution. So if we are interested in measuring traffic that relates to World Wide Web, or if we are interested in proposing any research in this area, it's important that we keep in mind the research findings, because we should be subjecting our algorithms to these workloads because they are most realistic as we understand the traffic now. Let's talk now about some other applications. Let's talk about DNS, the domain name service. The domain name service is a protocol that runs at the application layer protocol, but it's not an application that users interface with, in the sense that typically they use it to get some other service. They use it for resolving names to IP, but the clients do not intend to come to the DNS server per se. In the sense, this traffic is controlled traffic. So the first study on this area was done in 1991 by Danzig, who studied two 24-hour traces, and he discovered many DNS errors. And one important point I'd like to highlight here is that it is only through these measurements that we are able to detect buggy implementations and problems in protocols. In many cases, it was only after instrumentation and measurement that we came to know about various problems in protocols, and various improvements were then proposed, leading to a better internet. So it's very important that we give measurement its due right and its due importance. So Danzig in 1991, he discovered that DNS has lots of problems, and one of the most important problem he saw was that DNS, there was continuous looping between two servers, in which one server was sending the query to the other server and the query coming back. So to address this issue, then DNS implementations then put something of a TTL, in which beyond a certain point you would drop the query if it was continuously looping around. In another research study, the Border Gateway Protocol, BGP, was studied by Craig Lebowitz, who discovered that there are many pathological situations when we study the traffic which is created by the BGP protocol. And here pathology means some sick event in the sense that something that we do not expect. So just let me give you some background on BGP. BGP is an inter-AS routing protocol that runs between various autonomous systems, and it is the glue which is connecting the internet together. Every time we want to exchange routing information with another AS, we use the BGP protocol. BGP protocol was designed to be an incremental protocol. If the routing status at your router has not changed, you should not be inundating your neighbors with unnecessary information. But it was observed by Lebowitz that in many cases, many duplicates and many redundant messages were being received. And in fact, he estimated that 99% of the traffic was like that. And there was a huge log of traffic which was coming, which was totally unnecessary. So this was close to the year 2000, and based on his recommendations, many ISPs actually fixed their implementation of the BGP routing protocol because some of their routers had buggy code. And beyond that, even suggestions were made for improving the BGP routing protocol. And this is why measurement-based research is so important, because it brings to the fore many points that we would not know if we were doing just modeling and simulation-based studies. Let us now talk briefly about the research which has been done in understanding the Internet's infrastructure. The first thing is equipment properties. While there are many things about equipment like links and communication equipment that we can understand due to the way they have been designed in an engineering sense, but routers are more complex, and the minimum router delay, which is a function of all the processing that has to be done on the after receiving a packet and then it has to be forwarded, it has been shown that this has some variation. At the minimum, typically this is of the order of 20 microseconds. So, and beyond that, if you have traffic coming on one interface and it has to be sent on another interface using some other technology, then the time for the router to process it is typically larger than this. An important infrastructural research area is how do we map the topology of the internet. And in fact, it's remarkably hard to do that because the internet does not remain the same. In fact, the internet in the morning is not the same as the internet in the evening in all probability, because there are lots of changes all of the time. So many local changes are taking place, new links are being added. So any attempt to map the internet topology is doomed in the sense that it will never be complete. But still a lot of work is being done on mapping the topology of the internet in terms of the AS to AS connections, which we would call the AS graphs, where AS are autonomous systems. And then at a more finer grained level of detail, we can actually make a graph of routers within the AS. But this typically is difficult to do because many ISPs are not very keen on exchanging the information of their internal network. But there is a project Route Views in which we get information about the BGP routing table. And on the slide you can see the connections of the ISP, which is PTCL, Pakistan Telecom Corporation Limited. And this is a little dated, but you can see that how PTCL is connected to many different upstream service providers. In turn, it would be supplying a lot of customers, but it would not have a lot of downstream autonomous systems. But it has some upstream service providers, autonomous systems, through which it is connecting to the rest of the internet. One thing is that if we use simply BGP to map the internet, we are bound to get an incomplete structure, because using just measurements at a single place, we cannot have information about all of the internet. So there is a lot of ongoing research work in this area. Also, if we want to characterize the AS topology graph, we would see that it has been shown in various studies that it follows more or less a power law kind of a graph, and it's not the typical uniformly random distributed graph. And you can see that on the slide, the power law graph on the left hand side has a distinctive shape to it, and most of the AS connectivity graph would be like this. And this kind of a network is known as a complex network, in which not all of the nodes have equal outgoing degrees. Many of them are connected to just a few other autonomous systems, but some autonomous systems have a lot of other autonomous systems as their peers. Another important research area in which we are trying to find about the infrastructure is known as network tomography. You can see on the slide, the basic idea here is that we want to use the end-to-end measurements to understand the internal topology and the delay loss characteristics of the internet. And one major application of this, which is of a lot of use to internet service providers, is traffic matrix visualization. Such calculation on the basis of packet captured data would be very, very hard because of the amount of traffic that is exchanged. Instead, using end-to-end measurements, we infer about the characteristics of the network. And this is also known as OD flows, the origin-destination flows, in which we can estimate how much of traffic is moving from one ingress point to another egress point. And this area was pioneered by AT&T, the tier 1 ISP which we've talked about earlier, and it has led to significant saving for them. This was implemented in 2003, and some work has followed after that. Okay, let's move now to the second part of this session, in which I'm going to very briefly talk about some sound measurement techniques that have been proposed by Vern Paxson. Okay, so the first point he makes is that internet is tremendously diverse, complex and dynamic, something that we've already covered. And because of its diversity, we are desperate for invariants and parsimonious models. And parsimonious models are those in which we require least number of parameters. Because of the diversity of the internet, we don't want a model which is too much customized for one particular data set, because the data sets are going to vary around, but the basic invariants are going to remain consistent. So we want parsimonious models to model the diverse and heterogeneous nature of our internet. And also something which he knows a lot about, Vern Paxson, because he has done a lot of good work on internet measurement, is that sound measurement requires a lot of discipline and a willingness to consider that you might be wrong. So if one goes with preconceived notions of what results one should be expecting and one would be getting, then typically it biases what we infer from the results. Similarly, just as we should be ready to consider that we may be wrong, we should be skeptical about the claims of other people, and we should try to replicate their findings. And only if some result has been replicated by many different parties should we actually give a lot of confidence to that. Another important point is that network traffic is highly structured, and we should understand the structure, and if we do that, we can model the network in a more complete sense. And in a recent SIGCOMM conference in which Vern Paxson gave a keynote, he made an interesting observation, and he used the Google Scholar tool. He compared various search terms, and he saw that network packet system, network packet performance have a lot of articles, lot of research articles about them. But calibration is very low down on the list. And he compared this with the discipline of physics, and he saw that calibration is used 39 times more there. So the idea is that we still have a lot of way to go for internet measurement to become a science. Because in science, whenever we make some new result, it has to be calibrated. We, even during the process of doing scientific studies, we need to calibrate our result. We should be checking for self-consistency. And these are very important points that we must always keep in our mind when doing internet measurement study. Okay, let me conclude this session now. I've talked a lot about how important internet measurement is. Internet measurement has now matured to be a complete discipline. And it was a little hard for me to complete an overview of the major findings in just 2 sessions. But I hope that I have conveyed some of the most important points in this area. In the course guidebook, you would also find some pointers to other important work which I may have missed in these 2 sessions. So I hope you enjoyed this discussion. Till next time, Assalamu alaikum wa rahmatullah.